Uh, my name is Gumerov, and this is joint work with Ramani Duraiswamy, which is my colleague, and with whom we're working both in Institute for Advanced Computer Studies, University of Maryland, and Fantalga LLC. This is some company which where I was principal investigator to accomplish NASA-sponsored project on porting of the FMM algorithm on the GPU. So this talk is just about this experience of how we ported that and what we achieved, and that is the outline. So after a brief introduction, which maybe I already did, so this will be what is the fast multiple method. Maybe it's not, just very briefly. Then this about some experience, what is FMM on the GPU, and conclusions. Oh, should be louder. Okay, we'll try. So about the FMM, maybe I should not speak too much about this to this audience. Moreover, the chair of this session is one of the inventor of the street codes, and actually it's maybe first publication. Then appear several publications related to other kind of hierarchical algorithms like FMM, and basically what is important, so they reduce this complexity to this kind of complexity, and now it's a lot of publications, and we also teach some course in the University of Maryland for this FMM. So what is this algorithm? Is just like it's designed to provide some matrix vector or sum like this, and of course you cannot do this for arbitrary matrix. So it should have some special structure. For example, if you have this say gravity forces or electrostatics, so with this kernel or maybe some other equation. So in this case you can do something faster, like for O of n log n complexity to compute this sum, which otherwise requires O of n square operations. So the main idea here is in FMM, again very briefly, that if you have this matrix vector product, so we decompose the matrix to dense and sparse part, and dense part is nothing but just if you have some particle here, so this is all the particles in the neighborhood which you can evaluate directly, so it's direct summation of sparse part. And all the FMM, all the trees about how to take into account the contribution of all or interaction of all other particles with this given evaluation point or particle. So, and there's some theorems which just basically I will not go through all of them because of they say very simple things, that this potential can be locally expanded kind of Fourier series, or in this case in the sum of spherical harmonics locally, this basis functions, or it's sum of multiples for far field. And actually we have what we have here, this error of expansion, which is controlled by this truncation number p, which is important for this FMM algorithm. So this for any given precision, basically you can select some p and achieve this precision, and particularly you can achieve machine accuracy if you want, and in this case basically your algorithm, which otherwise is looks like approximate, will be at least not less accurate than machine precision. So and realization of this contribution of all these far field points or interactions is just like through several steps. It's one is just like if we have some sources located in this box, so we can build the multiple expansions which are valid in this dark gray area, then or this multiple is called S expansion or singular expansions. Then the next step is we go in octree. So here is quad tree, but actually we have 3D, so it's octree, and we can actually to translate all these expansions to some new center, which is valid for new far field outside this bigger domain. And then the next step is downward path. So we go up to tree. In this downward path, we do some translation, which we convert this multiple expansion to local expansions, which are valid inside, say, this sphere, and basically we will use them just for points which are inside this box. So this is contribution from some domain which is a neighborhood of the parent box, excluded the neighborhood of the box itself, while the contribution of all other boxes, which are like white here, it's taken by some translation operator of this local expansion to this box. So, and we hierarchically go down, and in this case we can go through the whole tree. So as you see from this algorithm, it involves some data structures, and basically this octrees in 3D. It requires different things like list of neighborhoods, indexing, and so on. And basically this operations at this point, we are working on that, and it's pretty difficult for them to map efficiently on GPU, and the algorithm which I'm speaking right now is still done on serial CPU, and we're working on that, of course. But even though that in many problems, actually, this generation of data structures, say if you solve iteratively linear systems, so you need to compute or generate this matrix or generate this data structure once, while the cost will be amortized over many computations. So maybe the relative cost of that it's not so can be somehow amortized. So what is important now is what is the complexity of this fast multiple method. So for dense part, when we compute this, so this cost is just is sum of this cost of generation of expansions, which is proportional to the number of sources, and the cost of all translations, so which is proportional to the number of boxes. So if you have a total number of particles and S number of particles at finest box, so in this case this will be approximately this B and A some constants. While the sparse part is just proportional to the number, this is number of particles, and S is the number of particles at the finest box, so it's just interaction of particles, it's its local neighborhood, so it's O of n, and basically it's also O of n, but we have some S which is kind of clustering parameter or number of particles. So, and if you want to optimize this FMM on CPU, basically we need to achieve the balance in the tree. So when this expression takes some minimum cost of S, and you can just differentiate and find that it has one local minimum and is optimal, will be like this, and this determines the maximum level of the octree which you use. Now, concerning the programming on the GPU, of course, there's some kind of, I don't know, everybody was supposed maybe to say something about experience. So what we can suggest that before doing some complex algorithm, maybe it's good idea to do some profiling, at least determine what are the relative contributions of different parts and so on. So what is the most important parts to do first? Of course, we need to remember this law. Then, despite we have some kind of libraries like QFFT, QBLAS, and so on, of course, we need to write at this time this kind of efficient subroutines if we want to really to get some kind of higher performance, because of that library is of course limited by some standard functions, and maybe especially for such algorithms it's not applicable immediately. So, but in our approach we also use this middleware, which as Bill Dorland taught earlier today, substantially eases the transport of Fortran code to the GPU, and we need to have some prototypes and in Fortran before doing that. So this middle, you can see poster. I will not stop too much in details about this, but idea is that anyway it's similar to CUDA somehow, because of its actually layer on top of CUDA, and it's the main flow is executed of algorithm on CPU, and it's calling GPU functions. So this is anyway this is something, and all these GPU functions should be written somehow carefully. There will be poster and details will be there, so if someone is interested in this library and how it works, so you're very welcome. So the FMM on GPU, of course, there are a lot of challenges, and actually what we found, this is what's important, is this GPU architecture substantially influences this even FMM complexity and optimization and how the FMM works. So then I will speak about this accuracy and performance maybe very briefly again. So among these challenges we have this complex FMM data structure, and which of course is not designed, the idea of SIMD, like all this technique is not basically natively designed to handle complex data structures, and it includes the non-uniformity of data because of our particles or stars or whatever can be distributed extremely non-uniformly. Then if we generate some expansions, say multipole or local, we use recursive computations, and this again should be thought how to do this in good way when you have this massive parallel process, so it's not sufficient. So, and then of course we need to take into account these different memories and bandwidths to make something efficient. So several talks this morning already addressed this issue about the direct summation on GPU, and this is our experience and measurement. So it's actually what we did. You see this linear, or sorry, this n square, because of, so it's log coordinates, and we got speed ups of up to 600 on GPU compared to CPU. Of course, this may be not good number because of its kind of naive implementation on CPU, and this factor can be not 6 because of its just serial code. I mean, no use of any kind of caching, unrolling, and other tricks which in principle can improve this performance. So this is just like two nested loops executing this n square interaction. So, but what is important now for, namely for FMM, it's how not the direct summation, but sparse matrix vector product can be computed. Because of behavior is very different. Look here what happens on the CPU. In CPU, when we change the level of octree, we have some jumps. But inside this level, this is n square complexity. Overall, it will be O of n, something average, but n square for each computation like this. On the other hand, if you compare this with the GPU input, it looks like this kind of step function. So what does mean that? So inside the level, the complexity or time to compute this problem almost doesn't depend on the number of particles. So but what it depends on? It depends on number of boxes. So and basically, so we have now, instead of what we have on CPU, this time is proportional to C, and as it will be proportional to the number of particles, which is read-write operations. Access to box data, it's number of boxes n over s, and this actually finally just float computation. So for CPU we have just float computation, but substantial overhead is created because of random access to box data on GPU. And this can be like what's in our algorithm we implement. It's if you have so sources and receivers in FMM can be different. It's like evaluation points and stars. So we have storage, hierarchical numbering and bit interleaving allow us to store data in such way that all data located in one box, they're located linearly here. So this provides coalesced reading of all data. If you have, for example, this box, you have random access to boxes here, but inside the box, all data are stored linearly. In this case, it's you can use coalesced reading, and basically what has happened so for CPU we have this time for sparse matrix, dense, and so we have kind of time like this. But for GPU, time itself has some optimum, and this optimum depends on the number of boxes and number of particles, and basically on the number of threads, how we found, because of each block is optimal, iterative number of threads, say not 1 or 2 or not 1,000, it should be, number of threads should be like say 256 in the optimum, but basically it can be vary around this number, but it should be some number. And this actually determines how many particles one box can handle. So this optimization actually comes from the architecture of the GPU, not from the other things. And this results in some shift of this optimum. So and if we optimize and take this, as you see, it comes almost linearly, and we have kind of again some better. So and this reduces basically maximum level of the OC tree when using GPU, and this is very beneficial for other parts of algorithm because of it's put lesser weight for other parts. So for other steps, we got acceleration in range 560 if you compare the straightforward. But here we can compare with, speak about effective acceleration because of GPU itself. It provided different tree division its architecture than provides CPU. So if you compare effective acceleration for this algorithms, it will be 30-60 times. So finally, this okay. So this is performance. If you take of CPU and GPU performance at optimal set, so we have special settings for CPU and special GPU. For each of them, we do our best. So in this case, we have kind of this profiling of this, and if you see this improvement, it's overall like 56 times, but it's again tenth times. And parallelization methods, we depending on the procedure, is differently used. So for example, we can use thread per box, so this one thread handles box, or block per box, so say 256 threads handling this, take care about this box. So this is issue important, which are error in Direct and FMM sums. So if you see the GPU, so the round of error grows with number of sources like this. And this is basically different from what we see on the CPU, even if you compute with single precision. So perhaps it's related to some kind of, I don't know, not triple ecom, or maybe Intel do some better CPU accuracy. But in CPU, this error doesn't grow. But on GPU, this growth is substantial. And what is interesting then, that FMM actually algorithm is stable to this error, both for any case, and actually it provides better accuracy for say million size with this truncation numbers than the accuracy provided if you do this sum directly. And this is some just charts of there was some kind of desire to achieve 1 million particles, million interaction for 1 second. And so what is our thing? We basically, if you see these numbers, we somehow achieved this for some accuracies, and all these numbers of order of second, million by million interaction. And this is speed ups for compared to serial codes. So yeah, so here some graphs also showing this is linear, and these improvements. I will not speak about this too much due to lack of the time. But what is this speed up now? If we can speak about speed up. So we achieved this speed ups. We evaluate 25 to 50 teraflops compared to serial code. Of course, nobody will compute directly a million particles on CPUs with serial code or interactions. But if you compare with that, so it's actually speed up provided algorithmic speed up due to this FMM, and speed up due to use of GPU. And each of them, it's maybe 100 times, and this result in such numbers like 25 to 50 teraflops, so which allows to compute million particle interaction for 1 second. So this is maybe the end of my, so this conclusions. You can read this, but I will stop this talk. If you have some questions, I will be glad to answer.
Have you played with techniques like compensated summation or higher precision? There are ways of using multiple floating point numbers together to increase mantissa for doing outer parts of the summation loops, things like that. It would be a relatively small speed shift, but it might increase the accuracy of some of the summation.
We didn't try this, but
Could you repeat the question?
So the question, what I understood is, if we used any kind of techniques which increase the representation of the numbers to increase accuracy, right? So, but we didn't have this problem basically if we go to FMM, because if you see FMM is stable and actually it reproduces exactly machine accuracy. We cannot go more than single precision. But if you go to direct summation, of course the error grow, but we do not proceed in this way. You can, if you see this where the direct summation becomes about the same rate as FMM, maybe 100,000 size. But if you go to million, it's already, in our opinion, it's more preferable to use FMM both because of speed and accuracy. Okay.